Thanks to Howard for inviting me to this interesting place. It's always inspiring and very nice setting to discuss. So I'm going to talk about conformal extensions of the standard model. And the main reason is that we have to think about new things different from the way we thought about electroweak symmetry breaking, because essentially we found nothing that we expected. It's, of course, you can take the attitude that it's just wait longer, new physics, your SUSY party is just around the corner. But maybe there's actually a message in that, and that's something I try to discuss. What do you make out of the situation if you had to live it as it is? Of course, it doesn't mean that it wasn't worth the LSD. We learned really very important lessons that should be emphasized. First of all, the standard model with neutrino masses works perfectly. It's a perfect quantum field theory. It's a triumph of concepts that go in there. Quantum field theory, symmetries, precision, etc. The Higgs boson was discovered, which is connected to explaining particle masses. There's nothing else so far, but the quantum structure of the standard model, which is very essential. It's consistent, it's there, it's tested, and I think that's measurements which should be highly appreciated. But then, of course, for decades, we had many ideas for new physics, and so far, nothing showed up. So that's why, as I said, things might be different, etc. And of course, it's always driven by experiment, means you have to follow what nature has in store. We had neutrino masses, so you have to explain large mixings that most people did not expect. There is dark matter out there in ways which people didn't easily expect, etc. So one should take these standard experimental facts, trigger, enforce new ideas. So what do you do? So first thing when you do something like this is to make a step back, look at your starting point. Don't dwell off into things that aren't established. Just go back to the basic, to the roots. And the roots are essentially the standard model. That's what works. It's itself a fully consistent quantum field theory like QED. It has infinities. We know how to normalize. That goes back to the basic commutator that you didn't take care of when you defined the theory, etc. One of the consequences of quantum field theories is that they only can calculate differences, never an absolute mass or coupling, and you promote the problem by embedding into other theories and hope that the next theory explains it. But you know that a quantum field theory would never explain that, because that's a generic feature of quantum field theories. Itself, it's perfect, even though many things are unexplained. It has also, like QED, a so-called triviality problem, which is the fact that there are real lambda poles beyond perturbation theory, so it's a consistency problem. You have to avoid it somehow. It means there must be some sort of embedding somewhere that takes care of it, otherwise the standard model or QED alone could not be the ultimate theory. On the other hand, you know there's gravity, something has to happen anyway, so you can put it aside a little bit, etc. The physics that's going with this new scale is, of course, unknown. It could be an explicit scale, it could be effective, it could be quantum field theory or new concepts, like when you go to quantum gravity or strings, etc. You talk about new concepts, etc. You don't know it. Another problem is this vacuum instability, that the potential may flip over, so that our vacuum is not the right vacuum, and they shouldn't be doing heavy ion collisions where you produce a bubble the size of a Higgs mass with an energy density too big, etc. It occurs for the standard model for large top masses, which is amazingly fulfilled, and gives you a lower Higgs mass. But the essence is that the standard model is a quantum field theory. That would be everything. It works perfectly up to these triviality issues, etc., and you could live with it. So why are we unhappy? We're unhappy because we think there must be new physics to explain things which are unexplained. That's why we usually embed into higher theories. The way it usually goes, the naive hierarchy problem, you do some cutoff and then you get these fake quadratic relations, etc. But of course the warning is that lambda is not something that's a cutoff of physics. The cutoff is in the brain, if you want to say. In nature, the cutoff is some embedding, some new physics that takes care of the degrees of the standard model embeddings. Either quantum field theory or something else. So this could be a form factor. In fact, the different loops could have different form factors. Could be heavy masses, etc. So it's some unknown new physics that we didn't spell out yet, and it's not this trivial cutoff. So you should think a little bit more about it. The real problem is actually that there's two scales. If you have two scales, then you run generically into a quantum field theory problem, namely that vastly separated two scales are unstable. The simplest way to see it is to have two scalars, little phi and capital phi, with little and m, with a hierarchy in the masses, etc. Unavoidable, there's this portal term because there's no symmetry that protects it. And when you do calculate quantum corrections, the light guy wants to be heavy, it's drawn to the heavy guys, saying that the quantum corrections don't support a scale separation. That said, you know that in the standard model a Higgs boson exists. So the problem arises once you start embedding in a second scalar. So when you do gauge extensions, you must break them, so you need a second scalar, the problem is there. When you go into guts, there's more scalars to break the gut symmetry, again the problem. It's even there for SUSY guts, because when you do supersymmetry and go into SUSY guts, you have to explain the doublet triplet splitting. So it's back, and you have to do something else to solve that problem. So it's not really solved in SUSY, if you're honest. It's also true for fashionable Higgs portal scenarios, etc. So what are the options? One option is to have no second Higgs. Then back to standard model, it's just boring in some sense. Some symmetry, of course, supersymmetry has been heavily discussed for many years. And I'm going to push into the direction of conformal symmetry. And I tell you that there's something interesting that might be worth to follow. Actually, there's another hierarchy problem, which I call the neutrino hierarchy problem. There's, as I said, these two problems, namely, and the standard model was Higgs says before, if you introduce Dirac neutrinos, there's no problem, because that's just a standard model with fermion masses added like for the quarks and charged leptons. But once you talk about Majorana masses and there's no symmetry forbidden, you have now a second scale, namely the Majorana mass scale, and it generates a hierarchy problem. If you do the loop calculation, you get shifts of the Higgs mass which go proportional to this. So even though the Yukawa coupling is tiny, it is a problem once your Majorana mass is bigger than 10 to the 7 or 7, 8 GeV, which is well below the favorable leptogenesis scale where you think you solve something. So you solve something, but at the same time you would introduce a new hierarchy problem that didn't solve, again, because you introduced a scale that's not acceptable even though there's this tiny Yukawa coupling. So, all that said, what's the way? What's the idea? Do not introduce two or more fundamental scales. I think that's the message for me. So the idea that I follow here is there's no fundamental scale whatsoever. You start with a theory without scale. You talk about conformal symmetry or shift symmetry. You talk about the dynamical breaking of conformal symmetry combined with electroweak symmetry breaking to generate both scales. So you talk about nonlinearization of conformal symmetry, such very much like in gauge theory, when you look back when you had vector boson mass into loop calculation, that didn't make sense, that diverge, until you learned the Higgs mechanism, saying that we have gauge symmetry and realize in a nonlinear way that the naive power counting is wrong. And that's what you do here. The naive power counting that we do these days may be misleading, and it may be very similar to the case of gauge symmetry and the Higgs mechanism. So that's easily said, and you could say, is there anything pointing in that direction? In fact, I claim that nature must be pointing there. If you look at the famous metastability, that's the famous plot, you know, that's our version, actually was earlier, but not publicized at CERN. There was this remarkable coincidence that you're close to this metastability bound. There's, of course, the discussion how many sigma we are, and I claim the errors are a little bit bigger, but let's not dwell on that. Independently of that statement, how close we are, there's a very important observation that this has nothing to do with the metastability. Namely, there's a remarkable relation between the weak scale, the top mass, and all these couplings, and the Planck scale, or a high scale. And that's actually a relation between these variables which is at the level of below 1%, few per mil. So you should ask us, why is it that nature chooses parameters at the level of few per mil that almost coincide, which they shouldn't? Maybe there's a message. So there's also a remarkable interplay between gauge Higgs and top loops, and that's the log divergence, the beta functions of the theory, and not the quadratic divergences. So maybe the log divergences have more meaning than the quadratic divergences, so that's something you should keep in mind. Now you can invert this statement even more provocatively, namely if you take the Mexican hat potential, the famous one, and run it as it is in the standard model up to the Planck scale or a little below, your potential is flat at the level of per mil. And you should say, is that an accident, or is nature telling you something that you could interpret? And of course, the interpretation that's to me obvious is you turn a statement around, you start with something like that, run it down there, and use that to explain that in the end of the day. So that's the idea, to start off with no mass scale, no lambda, with a potential that's really trivial at high scales, motivated by this conformal shift symmetry, run it down and break conformal and electric symmetry in a combined way. So that's the program. And of course, when you start off this way, you immediately run into questions that you should address. Here's a list of questions. The first one is, isn't the Planck scale that is out there a generic problem? Because there is a scale. You have to live with that, and you cannot go to the scale invariant, etc. thing. So it's, of course, the point that, as I said before, Renommer's quantum fields don't have cutoff, so the Planck scale per se is not a cutoff, but it's an explicit scale, at least it looks like this. And if you want to follow that path, you have to do something about it. And the way I would say you should go about this, that you should talk about the nonlinearization of conformal symmetry also for gravity. Means that the Planck scale itself should be seen as a scale generated out of conformal gravity, so that the starting point is really a conformal theory whatsoever. That's of course a different program, and I will not enter that because even there's some discussion how much the conformal symmetry still protects your etc. divergences. If it's in what sense it could even be renormalizable, etc. And so it's a long discussion. Here I will simply assume that this is possible, that the Planck scale up there could be generated as a scale. It's not like a hard cutoff in the low energy theory. Then you can go on, ask yourself if the Planck scale and the weak scale are eventually connected. You could have this. There's actually interesting ideas how it could happen in ways that I can discuss over coffee if you want. Here, where the rest of the talks, I assume there are independent scales, that there are two scales, there's conformal sectors you start, like in the old days when people discussed tumbling theories, that there's sectors which generate their scales, like QCD generates a scale, so there's different sectors of theory generating their scale, and there's two of them, so they're in some sense indirectly connected, but directly. Of course, the final theory should be asymptotically safe, so you have to talk about UV fixed points, which I will not do because of time. And there's also a very important conceptual change for scale setting, if you believe that. So far, we have been discussing embeddings into guts, whatever, etc., and so on, ultimately into quantum gravity, and the hope is that some concept beyond quantum field theory sets a scale that is transferred down to eventually explain your electron mass, your top mass, your couplings, etc., absolute scales, which quantum field theories can't do. Here's different. I give that up. I say there is no scale if you follow that route. It's only scale ratios, very much like in Cairo QCD. Cairo QCD has no scale whatsoever. You run it on lattice gauge theory calculations. You calculate the ratio of the pi and the proton mass. That's all you can do. You do one measurement to nail down your scale, and then everything else is fixed. That would mean that there is no basic scale to begin with. All scales are only scale ratios, and they're normalized in some way to a measurement, and that's it. I find it actually conceptually even more interesting than the usual way of having some scale from nowhere, and that feeds into all these things. That's quite a change if you follow that. Now if you go on, then you have to do nonlinear realizations of conformal symmetry. So you think of a like let's say the usual famous scalar propagator. Naive power counting will tell you that's quadratically divergent. Now what I tell you, if this propagator is a nonlinear realization of conformal symmetry, like for a W propagator being a nonlinear realization of gauge symmetry, you should not do the naive power counting. If there's a nonlinearization of conformal symmetry, the naive counting is wrong. It's similar to the vector bosons, and the sensitivity that's left is only log sensitivity, which is of course connected to the conformal anomaly, which is the beta function, which is running exactly what you need. It fits together very nicely. It avoids, in that sense, the hierarchy problem, and it means that the logs, the beta functions, remember the vacuum instability, are the dominating function. It's very much like in, let's say, in QCD. Cairo QCD, you then talk about dimensional transportation of conformal theories. In fact, Masters QCD, Cairo QCD is scaleless, and you run it and you generate lambda QCD and there's a spectrum out of it, etc., and so on. Note that you can also talk about scalar QCD in the same way. If you have massless scalar QCD without any scale, it still does confinement, it still does scale setting. There's no hierarchy problem because there's no embedding, no scale where you have to worry about where you cut off, etc. So it's fully consistent in that sense. Now, the simplest thing, the simplest way to realize that could be the standard model stripped off by the mu term. It's very important that the standard model has only one single scale, mu or the VEF, whatever you call it. There's only one scale. Everything else is dimensionless coupling. So all masses are dimensionless coupling times the VEF. If you set mu to 0, the standard model has no scale. It's very simple. So just drop it. That's the first thing you could do. That's old. That's the old Coleman-Weinberg effective potential calculation that you do. Coleman-Weinberg effective potential is actually dimensional transportation. It generates symmetry breaking, but only for certain parameters. The top mass has to be below 79 GeV, and the Higgs mass would only be 8.9 GeV. That's double excluded because the top is heavier and the Higgs is heavier. This would actually conceptually realize what we do, but as I said, it's just double excluded. It's actually an interesting lesson to be learned from that first calculation, because it shows you that dynamical symmetry break can happen for weak couplings. The point is that conformal symmetry puts you at the boundary between broken and unbroken theories, so any weak attractive force puts you in the breaking regime, so you get dynamical symmetry break for weak couplings, unlike in QCD where you don't have a scalar where you have to condensate first to get the breaking going. This also explains why the Higgs mass is so much lighter, because the curvature of the potential at minimum is a loop effect, so it's naturally down by 1/16 pi squared. So in this scenario, you know that when you do this, you automatically get a Higgs mass that's a 1/16 pi squared down from the generic scale where you start from. That's why it doesn't work in the standard model, because the Higgs would be too light. And don't forget, we need to add neutrino masses, dark matter, and all the other stuff. Now with those lessons learned, you can go back and work your way and generate a whole class of models that do what you want to do. Then you just have to take the fact that you know the Higgs mass, and this 1/16 pi squared tells you that the scale you should be starting from is TV-ish. And then work your way back and realize it. The way to go very systematically is to use so-called Higgs portals. If you have the standard model scalar and some new scalar, or even more, and you assume everything to be conformally symmetric, so no scale whatsoever to start with, only the potential terms, then from symmetry there's no way to prevent the portal terms, so you have these portal terms. So if any of those new scalars in a hidden sector produces a condensate, then the mixing term acts effectively as a mass term for the electroweak sector, breaks the electroweak thing. So the breaking can happen with this new sector. That's what it does. So you do the conformal symmetry is anomalous, you run it log, etc., blah, 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 and so on, and they could generate a hidden scales, and then you get the condensate with the right numbers as you want it. Then you have many model building possibilities. In fact, you can write down many things and discuss all sort of phenomenological aspects that go with it. So phi could itself be an effective field of a hidden sector, could be composite scalars or fundamental scalars, etc. Of course, many further particles could exist in hidden sector. It could be fine. You can discuss tumbling or hidden technicolor and things like that. Once you add it, there could be extra hidden U1s, but they would be problematic because of U1 mixing typically. So you want to avoid that. And of course, you want to avoid Yukawas which couple the visible and hidden sector. Otherwise, you're phenomenologically very safe, because everything that's new comes via the Higgs portal, the Higgs self-coupling that we haven't measured yet. So if you do this, you say, even though it's deviation of physics, but it also means that the things you put in there are not so far away from being experimentally accessible. So it's actually not as bad as you think when you think there's no scale, everything could be high. No, there's something not so far around the corner. So let's realize it. And the very simplest realization of that actually was with Cooper. We had actually a very interesting exercise, which I call the most simplest one. Don't introduce anything but a new scalar. Take a standard model and take a new scalar. That's a color representation on a QCD. So then you write down your gap equation. The propagator has a self-consistent condition. The usual thing is the running alpha times the C2, the second Casimir of the representation, has to be bigger than a critical value to trigger the gap equation. Don't forget that this is a scalar gap, so it's enough to have a relatively weak coupling, etc. You write down your Lagrangian, etc. And you do this, you run your lambda QCD, and since the C2 is larger, you need a smaller alpha to trigger condensation. And that's actually an exponential enhancement of the scale, because log running translates in the criticality condition inverted into an exponential amplification. So if you take the right representation, you're done. And what you have to take is maybe, you may like, is a 15-plet. If you take a 15-plet, the condensation happens at relatively low values of alpha, while if you have a quark triplet, you have to run down all the way to lambda QCD to get the condensation. But if you introduce what I just said, this QCD 15-plet, then there's in the QCD sector condensate forming at high scales, exponentially enhanced high scales. That is this term, which then via the portal feeds over to the electroweak scale and gives you an electroweak mass. So that would mean a QCD would break the electroweak symmetry. That's what the consequence of, and all it takes is just adding one extra scalar with the right quantum numbers, nothing else, nothing more. Of course, once you know how to build a model like this, you can be more fancy. Well, it's the phenomenology, I skipped that. You can be more fancy. For example, you can do left-right symmetries. They have beautiful properties, so you go that. You take the usual left-right extension. The only thing you have to add to make it work, you have to take a spin 4 representation, so restrict the representation to a certain subset to make the potential do the right thing for you. And then once you're done, it works. It's not. The only problem here is you don't understand the framework why the scale separation between the left and right is there. It could be anything, etc. So you have to adjust parameters a little bit, not orders of magnitude, but factor, let's say 5 or 10, does it to get the electroweak scale and the left-right scale separated. It's not a fine-tuning, but it's the price you pay if you go that direction. Now you can go further. You can also well, that's the discussion here. They do this potential here, the most general left-right potential. You calculate the so-called Weinberg Formalism. You calculate these potentials, etc., and get what I just said. There's this 1 or 2 order of magnitude separation, which you have to explain by choosing couplings, etc. It's a moderate adjustment, but that's okay. Our next version is to take the standard model like a hidden asymmetry gauge sector. That's in some sense like Technicolor and hidden sector, if you know that. So it's a standard model, some new gauge group in the hidden sector, you write your Lagrangian, etc. And then you have again, in the hidden sector you get condensation, like in Technicolor, but then you have effective terms that couple to the weak sector to transform the scale that's generated in the hidden sector, TV scale, back to electric sector. We're done. The only way this physics talks to your standard model is via these Higgs portals again, so that's why I don't see so far anything at the LHC. It's systematically just around the corner. So you can calculate this hidden sector, use the similarity to QCD, do large N rescaling, or use number-general linear approximations, etc., and actually can do, I would say, semi-realistic calculation of the spectrum they expect, the phenomenology they expect, etc., and so on. But the main idea is, again, it generates a TV scale, hidden scale, and via the portal terms, it's fed over to the electric sector, etc. There's this also dark pions, which are pseudo-Goldstone bosons, which are naturally stable, which then turned out to be perfect dark matter candidates. So not only that you solve something along electric symmetry breaking, you can also easily get dark matter candidates if you look for that at the same time. I think you know how the rules of the game are. You have to introduce some portal term to some new sector which generates scales. That can be systematically followed, and there's been quite a literature now how people do it. Number of realizations, and I think there's also some missing, etc. That's the basic idea how you can realize this scenario in different ways. And it doesn't depend on the details. The main mechanism is that you have a scale setting mechanism, and the portal talks to the electric sector. So that's it for the electric symmetry breaking. Now, is there more consequences? And there's actually interesting consequences for dark matter, as I just said, but there's also interesting consequences for other things, like, for example, neutrino masses. When you talk about neutrino masses, you usually do this thing, you add these 3 right-hand neutrinos in the simplest version, you have your Dirac mass, your Yukawa couplings, you have Majorana mass terms, you get your seesaw, etc. And of course, there's quite some new ingredients when you do that. There's first of all, there's the Majorana masses are explicit new mass scales. That should ring a bell, because in the conformal framework, you're not allowed to have that. And of course, there's lepton number violation, and there's also conceptual changes because the global symmetries are affected. There's quite some changes, etc. And especially this first point, this Majorana mass case, has of course to do with conformal symmetry, and I'll come back to that in a second. Of course, you know that you can do it in different ways. You can add triplets or fermionic singlets or triplets and write these mass terms. Again, you add explicit mass scales. Or you can do more things, both things, the type 2 or 3 seesaw. You can add higher dimensional operators if you want, or radiative generation. In all these cases, you introduce explicit mass scales. And that's exactly what you're no longer allowed to do when you talk about these conformal extensions. So these explicit Majorana mass terms break conformal symmetry, and they would be forbidden in that framework if you follow this conformal symmetry route. Now, can you get neutrino masses? Of course you can get it. And he's studying the conformal framework with these young guys here. And this is a guy in our group that I put the J there because not Alexei Smirnov is not his son, he's not related at all, but Smirnov one of the most common names in Russia, and this young person still needs a career. Alexei has it already. So that's why I amplified his J always. He's a very good guy. So what we did is we said, okay, add neutrino masses and do no explicit scale. Means that there's no explicit Dirac or Majorana mass, whatever you add. You always have to check on that. You could usually write sometimes mass terms, but here they're no longer allowed. So the only thing that's allowed then is to add Yukawa couplings and generic scales. So we then extend the model field spectrum, like one of the gentlemen that's actually in the audience, to have a limited set of particles, and consider the direct product of the standard model times some hidden sector. And then you know from this symmetry breaking that you have 2 scales. One is the conformal symmetry breaking scale, which tends to be TV-ish, and the other one is the induced electric scale, which is somewhat below the electric scale there. And an important consequence of that setting is, in general, without writing details, that there's a spectrum of Yukawa couplings multiplied either with a TeV or electric scales. That's it. So you have some Yukawa couplings times those scales. So the Majorana mass terms are then no longer expected at the generic lepton breaking scale, but anywhere, because the Yukawa coupling can be a number that's 10 to the minus 6 or 10 to the minus 5, etc. Usually when you do this neutrino mass generation, the mass scale m, the Majorana mass terms, are considered to be identical or very close to the lepton number breaking scale, 10 to the 13 or some high scale. In this case, you have some lepton number breaking with some scalar, but there's a Yukawa coupling in addition, which changes the scale drastically. What it means then is you can do, for example, the seesaw, the standard seesaw now, in a way where the 2-2 element is no longer an explicit scale that you write down because it's not forbidden by symmetry. Now it is forbidden by symmetry, but you can write it down by a Yukawa coupling with a suitable scalar that has now in this breaking sequence of f. Now this f is TeV-ish, and the Yukawa coupling can be anything, which means that this term here, the 2-2 term, can be tiny compared to the Dirac mass terms, easily tiny, because the Yukawa coupling can be 10 to the minus whatever, right? We are used to the fact that because of chirosymmetry, Yukawa couplings can be tiny, while gauge and Higgs couplings are typically order 1. So this is now Yukawa coupling, so it's a tiny term, which means that you can actually naturally, out of the type 1 seesaw and conformal symmetry, end up with a pseudo-Dirac neutrino instead of a Majorana neutrinos. Essentially not. So that's what you get. Same, if you do it the same way, let's say for radiative masses, you get this kind of picture. Same thing. The terms where you had a Majorana mass term before are now replaced by one of the generic case times Yukawa coupling, and again you get this pseudo-Dirac case easily. We can go on to, for example, let's say inverse seesaw, same thing. It's very interesting. You can do it. There's actually very interesting consequences like trident production that you could see at the LHC, or natural suppression of delta beta decay against expectations, etc. There's quite a number of changes in this neutrino physics coming from that argument. And in general, I would say, if you do the usual neutrino mass matrix here, fill up the left and right-handed mass matrix with these extra mass terms here in the diagonal, the Majorana mass terms, you could usually would argue that all the lepton number breaking scales are high, while the other scales are electric scale, and that ML is 0. That's the usual game. That's where you get the seesaw. You can still get it, but you can get much more flexibility. You can get any neutrino mass scenario that you want. You easily can have cases where one of the guys is light, the two are light, the one is heavy, all of them are Dirac or pseudo-Dirac. So if you ever find a Majorana neutrino, Dirac neutrino, stereo neutrino in the, let's say, the KV area from dark matter or in MEV area, no problem. Here you can explain it easily, while the standard seesaw would have a hard time to understand it. So it's a very nice framework which would allow you to understand this kind of anywhere stereo neutrino mass scale, if it had to be explained. So I briefly mentioned dark matter. There's different ways to get dark matter because the chairman is done. I finish. So let me summarize. The standard model works perfectly so far. There's no signs of new physics, and there's two ways to attack it. One is to be a little bit more patient and pray and say and work your details of your conventional models. The other one is maybe it's time to reconsider and think about other ways to break the electric symmetry. There's the old hierarchy problem, which etc. And I claim that this metastability may be interpreted as a message actually pointing in that direction. Then we talk about embeddings into quantum field theories with conformal symmetry, which actually end up in a conformal and electric symmetric in a one combination. There's implications for BSM cosmology, there's implications for Higgs couplings for dark matter and for neutrino masses, and most of all it has testable consequences at the LHC, but also in neutrino physics and with some restrictions also in the dark matter case. So that's all I want to say. Thank you.
Well, I guess it's a question and a comment. It's a very nice idea. We did something extremely similar about 3 years ago with Bill Bardeen and Martin Bauer and company, where we use actually the dark sector being an SU2 cross U1 instead of an SU3. And there we didn't look at neutrinos, which is an interesting point. We look at dark matter, and we have some, we have some neutral dark matter, but we also have some lighter charged dark matter under the U1 dark. And so with some interesting consequence for.
Absolutely. I think.
So what is your situation? I mean, I suppose that you also have. I mean, first of all, did you know about this? Because the idea is very similar.
Right. No, in fact, if you go back in the literature, old days, again and again, somebody came and close to that, etc. So there's a richer literature where people try. But I think the new thing is now that we know more from electric precision data, from the metastability. That's why it's more specific now. But I agree, there is, so say, people had ideas which are pointing that direction, but didn't fully push it through.
But this is fully pushed because it was 2014, so we did know a lot about Higgs and.
No, I think the point now you can turn it around and say you systematically understand what you should do to make it work, right? And also can systematically explain what has to be yet to looked at. So the one thing is, of course, the Planck scale story, the conformal gravity, what it does, because the double pole and the power counting, etc., and all those things, I think they are clear now. While in those days, people just focused on the quantum field theory low energy part, right?
So what is your situation with dark matter, since you didn't have time to say?
Which one?
In your case, so what would be the dark matter candidate,
so it
and
depends,
what are other lighter?
So you can there's in this hidden sector case, you have these two Goldstone bosons of this hidden technical like theory, which are dark matter candidates. If you have neutrino masses, I can easily explain a KV star neutrino for you as a dark matter candidate. So there's quite some possibilities, etc., depending on the model that you do. And some of the models have no dark matter candidates, some do have it, and they can be. There's many options, I would say. There's no generic one, depending on what you do.
So what are the predictions in these kinds of models for the gravitational wave spectra? Is it the same as?
Here's the expert. He just gave this talk to that. No, I think there are consequences for early universe physics, how the phase transition goes, and that has, of course, I think, imprints on the gravitational wave spectra. I think was the talk that we just heard this morning, right? Again, I think there's a main route, I would say, but then if you tweak it, there are some side routes, etc. But I think there's some generic features that you would expect from there, and I think that's what was discussed.